So what we did just before the break was that we are now kind of on our way to the proof of perimeter law. Like there is a perimeter law when the dimension is larger than 3. And the first step towards that was to prove that the probability that you see a vortex, that is some kind of cluster of packets, at some given packet P, is kind of small. And if you could also say like the probability that it's larger than 2k, with essentially the same argument, you would say that the k is exponentially quickly in the size of the vortex. So that means that for taking beta large, firstly you can make it so that you don't have that many vortices, and secondly you can make it so that the ones you see are typically not that big. So there are two things you can do, and this is, remind you, used two things. The first thing we needed to get this exponential decay was that beta was actually not too small. So beta needed to be larger than something. Let's call it beta 0, because the other ones are beta 1 and beta 2. Maybe we should call it beta 3, because it should be larger than beta 2. You needed that to be sufficiently large, and this was to kill this first geometric term when we counted how many vortices it could be. So it actually needs to be not too small for this argument to even be true. The other thing we used, but perhaps didn't say explicitly, was that the dimension has to be at least 3 for this to work, because this was all using the property that vortices is something that appears within cluster together. And as you saw, they don't do that in dimension 2. So we have used both that beta is not too small already, and we have also used that the dimension is at least 3. So if you wanted to prove something in 2 dimensions, like you couldn't use this thing because it doesn't work, and if beta is small, when we expect area law, then you can't use it either. So we've already used both properties. But what this says then is that vortices are typically small. So I will not do this super formally, but I will tell you how to end the proof if you want to do it super formally. But rather I will try to give you the idea of why we should expect perimeter law. And then in the end, when I hopefully tell you how to do the area law, you will also see another way to do it that works very well for set 2 and is in fact much easier, but this kind of illustrates what happens for general finite groups, so this is nicer for that reason. So now say we have a loop, and now I will make it like super big, so that even you in the back will see my super big loop. So this is big. And remember what we try to do is that we try to calculate the expected value of the Wilson loop corresponding to this super big loop, which is kind of the product of the edges in the loop and the representation of sigma of e. This is exactly what it is. And we can write this in a number of ways. And the first thing we will want to do, so that's just to have it. We can continue, just remind you of it. That's what we're trying to do. And one of the things we did yesterday that I said would be useful was Stokes' theorem. And what Stokes' theorem said was that, well, this is the product over a loop. If you have some kind of surface with this as its boundary, then this will be equal to the same thing but instead with d sigma of p. And this is to some extent already a very good step, because as we've seen in all the pictures, there is nothing in this measure that kind of makes edges want to be 0. So we will have edges that are both 1 and 0 everywhere. So this is extremely noisy. So here already by going to Stokes' theorem, now we know we are in a setting where we don't have that many vortices. This should be a less noisy observable, because now we only have, like instead of having edges that are super, super noisy, we only need to worry about vortices. And in fact, we also only need to worry about the vortices that intersect our surface. And so this is like the thing, and we have to now assume we are in 3D, because this argument will fail drastically when we are in 2D. So we have vortices, and we said that they are kind of rare, but they happen. So we might have one here, and you have to think this is like Parkinson stuff, but this is the vortex. We might have a few like small ones. We might have a few larger ones, and then we might have a few that kind of are something kind of close to the loop. We could even loop around them. So a few ones at me. So this is kind of the situation, and we are in 3 dimensions. Now, the thing with Stokes' theorem, or the argument, like this argument is made nicer by Stokes' theorem, because now we have this thing, and when we started, it's very natural to think about a rectangular loop, and we can still do that. But when you think about rectangular loops, you're kind of tricked into thinking that this surface has to be flat. And it really doesn't. Like, you can have any surface. You can have a balloon-like surface. It could happen to have the boundary down there. You can have one that like nests up and down. And you can even have a very strange one with handles on it or something. Like, you can pick many different ones. That in particular means that if you have a lot of vortices here that are really small, instead of picking the like flat one that would intersect that vortex, you could kind of make it loop around them. That is by Stokes' theorem. So that means that if you are a vortex that are in here somewhere, that should not affect that observable, because this should hold for any choice of surface. It should be the same for any choice of surface. So I can be smart and pick one that, you know, pass through these very tiny things. And since they are like, we have an exponential thing here, they are finite almost surely, so that should kind of work. That would not work in 2 dimensions, because in 2 dimensions there is only one surface which has the rectangle as a boundary. But in 3 dimensions I have a lot of freedom to pick a very strange one. So I can in particular avoid all the things that do not kind of are close to the boundary. So if you're really, really far away, I can definitely avoid it. Heuristically, you can do this more formally, but heuristically. The ones I need to be worried about are the ones that are kind of close to the boundary. Because it's not obvious that I can avoid something that is very close to the boundary. But I can definitely avoid these ones. And if you like thinking about geometry, you can think about it as just pick a surface that avoids them. They are small, they are like super small typically. And even if one of them is kind of large, I can go around it more properly. So that's one way to think about it. The other way to think about why I can avoid them is that if I have a small vortex here, and I assume I pick the flat surface, and it happens to intersect that vortex. That might happen, right? Then we had the Poincaré lemma, saying that, well, if this is contained in a box, which perhaps should not be purple, because now purple is maybe moving stuff. Say this is contained in a small box, and since the vortex is typically small, assume that this is a vortex that sits in a box that is kind of far from the loop. Then by the Poincaré theorem, there is one form, also contained in the box, with that as its support. But if you think about that thing, then like we are supposed to do things over all the things in the thing there. So one part of that product there would be the plaquettes in that box. But if we just think about the product of the plaquettes in that box, maybe intersected with Q or something, so we really are there. Well, in that box, this is equal to mu, because that's the point with the vortex. So this is equal to the packets in there and rho of this vortex. Now, by the Poincaré lemma, there is some one form that corresponds to nu. It does not have to be sigma, it can just be anything. Some kind of one form that corresponds to that. That is contained in that box, and we can even assume it has 0 on the boundary of the box. It really has support inside the box. This is a small square, so it has a boundary. So let's call the boundary here, if this is our magic vortex we're thinking about, we can say that the boundary here is called gamma nu or something. Yes, we have the loop kind of corresponding to that boundary. Then this by the Poincaré lemma is equal to still the sum of the packets inside the box. But now instead we can have rho of the sigma of P. No, we shouldn't put it in sigma, so let's call it the sigma nu. So that's the one form corresponding to That by the Poincare lemma. Now what's good with this? I will move here. This is really a stupid way to use the board. Sorry for that. But let's do it anyway. So this will now be the same as the product over the edges is the boundary of this box. Rho of sigma nu of E. But this was chosen to be 0 on the boundary of the box. And I'm now taking the product over the boundary of the box. So this will be 1. So by the Poincare and the Stokes theorem, you can do this formally and say that, well, if I don't intersect the boundary, if I'm in a box that do not intersect the boundary, then the product of the paquets over that thing will be 0. This is to some extent exactly the same thing as you do in calculus. But this is a typical use of it. So this would be the formal argument for why we don't need to care about things inside the box. But the informal argument would be that we can really pick any surface, just pick one that do not intersect the vortices. So you can pick the argument you like the most. But the main conclusion would be from these things is that if you're a vortex that is far away from the boundary, you will not make a contribution. So that means that the only contribution we can have to the Wilson loop observable is from vortices that are somehow close to the loop. And they need to be so close to the loop that you cannot find a box that kind of contains the whole support of the vortex that do not intersect the loop. We need to worry about those, but the rest of them we don't need to worry about. So in 3 dimensions, that would mean that the dual kind of has to loop around the curve. But they really need to be close by. So that means that if beta is large, the only effect we will see that will kind of contribute to that thing will be from things that are kind of small and around the boundary. So from that, it's kind of not hard to imagine that this would give you perimeter law. It should somehow depend on how long the perimeter is. The area really shouldn't matter, because what happens in here will not matter. The only thing that will matter is what's close to the boundary, and that should give you some kind of perimeter law. Yes?
Since you want a lower bound, it's not completely clear from this viewpoint.
No, it's not yet completely clear at all. This is just the heuristic for why you should actually get perimeter law. So this is not like an upper bound or a lower bound. I've just said so far that you can skip things in the middle and only need to worry about things at the boundary. So this is kind of the heuristic idea for why it's reasonable to get perimeter law. And the same heuristic will work in any finite group setting. As long as you have the Poincare lemma and the Stokes theorem, you could do the same thing, just pick a surface that kind of avoids it. And then in that setting, you should get some kind of perimeter law region, because the only thing that will affect the loop will be things close to the boundary. So the reason this doesn't always give you perimeter law is that we're kind of using this idea that vortices are typically small. If beta is small, like too small, then this bound doesn't hold anymore, but also like you would have vortices everywhere. They will not be finite anymore. Most likely you will have some kind of vortex network that spans the whole loop, and then the area might come in. But as long as they are small and kind of finite almost surely close by, you will only see an effect from things that are close to the boundary. So now, as Christoph pointed out, this is not formal. And this does not immediately give you an upper bound. So then the question is like, how do you make this more formal? How do you kind of quantify this effect on what is close to the boundary? And it turns out that that's kind of tricky to do directly in this model. There are 2 kind of approaches you can see in papers from the last 10 years. The first one, which gives you something in this direction, is what is done in kind of a lot of papers, and it's called a dilute gas limit. And it doesn't really answer the question, but it takes you like one step towards the answer. So the first approach you could take to make this more formal would be a dilute gas limit. And this appears in several papers from last year. So this is what Chatterjee did in his first paper. And this is what was done in, I think, most of the subsequent papers that claimed something like perimeter law. So both the paper I have with Felix Liklund and KK18 of the Netherlands do this, and Sky Chow does this in his paper on finite non-living group. Problems all the time because this is the kind of easiest setting to say something precise. So the problem here is that even if we have like only things close to the boundary, they could still come in different sizes. And you could imagine these could interact in kind of horrible ways because the loop is really, really big. That makes it complicated. So you kind of want to make it easier because that's usually the good approach. So try to make it easier. And then the question is, how can you make it easier? Well, the general way to make it easier is to take beta larger. Like take it crazy large. Because if you take it crazy large, and you have this thing, it should say that, well, then almost everything should be small, and vortices should be kind of even more far apart, and so on. Problem is that we kind of want the loop to be very large. So it turns out that no matter how big you fix the beta, you will kind of see horrible stuff somewhere, because the loop is crazy large. So the idea with the dilute gas limit is to take beta crazy large, but not only take it crazy large, take it crazy large like in proportion to the size of the loop. So the idea is to take beta n. So beta will now depend on n. I take beta, let's see that. So that the length of the loop times, and now ask Christoph, I'm sure this will be wrong, because it will be 4 over 2 or something that's most likely off, minus, and I think we need 24 beta. Sometimes it's 12 in these papers, you sometimes see that, depends on the parameterization, and it also depends on the dimension. But I need to take that so that this is kind of approximately 1. So that means that if the loop is larger, beta has to be larger, because otherwise it will not be approximately 1. The reason you want to do this is that if you take beta to infinity, that will be super boring, because then you get no vortices. So you don't want to take beta to infinity. On the other hand, you don't want to take beta kind of too small, because then you see vortices of all sizes and it will be complicated. So the idea will be to take it just so much away from infinity that you will see something. So some vortex will intersect the loop. However, you only want vortices of the smallest possible size. That's the idea. So if you take them kind of exactly with this scaling, what will happen if the loop is really large is that then all vortices close to the loop will be minimal. And it's the smallest possible type of vortex you can get. And the smallest possible vortex you could get was a dual of the smallest possible interesting loop you can have. So that is the one where you correspond to having all the packets that were adjacent to some edge, which you like. So you will take it super small. So this is all you will see. We need one of those down here as well. This is supposed to be a 3-dimensional thing. I'm slightly afraid of turning on my computer again. So the idea is to pick them matching, so that the only thing you see are the minimal ones. Because if you only see the minimal ones, things will not be as complicated anymore. Because then they essentially follow a Poisson process of minimal vortices. And then you can kind of estimate these kind of things. So that gives you one estimate that kind of looks like a perimeter law. However, if you do that, it's not really obvious that it is a perimeter law anymore, because they depend on each other. You really want this for like all beta larger than 2 or something, and this is definitely not larger than 2 and need to scale. So that's one approach, and it's quite common to see it in these papers, because that's like the first easy thing you can do, because then you can at least say something. So that's the first thing you can do to make it formal, and this appears in several papers. The other thing you can do to make it formal, and I will just essentially just tell you the name, because if I would talk about this, I would need to talk about this for like 2 more hours, and I don't think you want to listen to me for 2 more hours. The other thing you could do, approach that kind of works, is what's called cluster expansions. Cluster expansions is like standard idea in statistical mechanics that usually appears in textbooks and so on. That works if you have a system of some kind of vortex-like structures that might interact with each other, but essentially you need that you can write a partition function as some kind of product over the weights of the vortices you see, times some kind of interaction function between pairs of vortices. As soon as you have that, you have something called cluster expansions. And using that, you can also make this formal and actually make it formal for like all data logicals and fixed data. So that's a two approach to it. But essentially, and both like that would give you a proper upper bound. This will give you some kind of idea what happens is like a first approach. But the general reason is that things in the middle won't really matter. The only thing that will matter is what's close to the boundary. So that's, I think, everything I will say about perimeter law, at least for now. And this is kind of the heuristic, but also like this is the understanding part of what happens. Because the proof I will show you now for the area law, which also kind of gives you proof for this. With that, you don't really understand what happens, and it also do not work for other groups except you. Did you have a question?
Yeah, so when you take the DU gas limit,
yeah,
somehow the way you have to scale beta depends on the loop.
Yeah, exactly.
But let's say, I don't know, you want the product of like, if you want to complete some correlation, then each time you want to complete a different correlation, you have to change the speed of beta.
Yes. No, I mean, so this is not optimal, and it doesn't give you perimeter law. So the first papers do not give you perimeter law. That's not what they're doing. But they're saying something, and it also turns out that this is like scaling like this. If you do that, then the Wilson loop observable will have a kind of interesting expectation. I mean, it does decay like the perimeter of the loop, but if beta kind of kills that parameter, you get some kind of number. So that was also one of the reasons this was done. But yeah.
For other finite groups,
yeah.
At this stage here, you used commutativity.
Yeah, I use commutativity, but I mostly use it because of Daisy. So if you look at Sky Chow's paper, for example, when he does a dilute gas limit for non-abelian groups, he essentially uses the same thing. So you essentially have the same tools. You just have to be much more careful at every step. So it's like it's a translation, but it's a non-trivial translation. But the same idea works. The point, as soon as you have a finite group, and beta is large, is that you will get some kind of gas amortices that are far apart and spread out. And you can pick any surface and then you can avoid them, and then you get perimeter law. So that's essentially the reason you get perimeter law as soon as you have a finite group.
So you're saying when it's commutative, you had these two IDs to say that they don't matter.
Yeah.
If it's non-commutative, only the first ID to avoid still works?
Yeah, I mean, the idea to avoid them still works, but then you need to worry about how to actually estimate what you have at the boundary, and that's not trivial. And it's not really obvious how you do it. I think cluster expansions would work if beta is sufficiently large still to actually give you a upper bound. It should do that. But again, you need to be more careful. And also, if you have a non-abelian group, you can't define vortices as just the clusters, because then they can interact in more complicated ways, and life is not as nice as it is if things are commutative. But essentially, the same idea gives you perimeter law. So this is like the driving thing that drives perimeter. And the main problem with Z2 is that then you can't move the surface. And hence you should not. Like, this whole idea is that you can essentially move the surface to avoid the things in the middle, and you can't do that on a two-dimensional graph, because then you have no choice of surface.
But why can't you do this Poincaré argument to somehow omit them?
That's a good question. Yeah, you can't do it because you can't talk about vortices.
Okay.
Yeah,
right.
So that's why. So here, like, you can define a cluster and then you can define the thing. But in a two-dimensional thing, it's not obvious, like, well, what would be the closed two forms, because things are just spread out.
Right.
so you can't match them up. So I guess you would have the same problem as you would have for the XY model in some settings, like if you can't match things up and then you can't use this framework. So in fact that wouldn't work, which is good. But I mean, in any case, you're also using that clusters are finite, and that argument didn't work in measure 2 either. So that's that. Now I'm going to say something about why we have area law. And the problem in this setting is essentially equivalent to the problem Christoph was having, to some extent. Namely that like this argument works very well, because things are kind of finite and nice and well separated and so on. When beta is small, this model becomes noisy. Like very noisy, you will have packets anywhere and you won't be able to distinguish this vortex structure anymore, which is of course bad. So usually the thing you want to do then is some kind of expansion or transformation or something to a model which is nicer. And there are several ways to do that. There are several different ones, especially for this model. And they are all kind of analogous to the same ones for the Ising model. So in particular, you need to say something about area law in a nice way. You need one of these representations. And the 3 cheaper one to use is either what's called a high temperature expansion. If you have seen that for the Ising model, it's essentially roughly the same. Like you do exactly the same thing. But since we have a different observable, we get something slightly different then. You could also use what's called a current expansion. That works for the Ising model and it works here as well. But it turns out what's nicest to use here is a third type of expansion that's called cluster expansion, which exists for the Ising model, and I guess at least some of you have seen it before. It's what you need to use if you want to use Swensen-Wang algorithm, for example, to sample the Ising model. And if you haven't seen it before, I think I will just write it on the board so you can compare them. So this is a very brief detour to the random cluster model. So for the Ising model, essentially what you do is that you do some kind of transformation, to some extent very similar to the one Christoph was doing. And the thing you start with, or like the observation all this always starts with, before you do some kind of magic, because Christoph was using a Fourier expansion, right? This thing we will use here as a start, and I will not do the whole thing at the board because that would take time. You would just trust me that if you try to copy the proof for the Ising model, it would work. So here the thing we're using is that if you have e to the 2 beta times rho of d sigma of e, then this is either plus or minus 1, and this is exactly what appears in our partition function, like we have a product of loads of them, or a sum of a load of packet. This is the same thing as e to the 2 beta times 1 minus e to the minus 4 beta, so some kind of transformation in beta, times the indicator function of d sigma of d being equal to 0, plus e to the minus 4 beta. So that's the observation you're using. It's kind of easy to check because the only thing it looks strange if you haven't seen things like this before. But the way to think about it is that this thing is either equal to 1 or equal to minus 1. So the only thing you have to do is to plug in 1 and minus 1. Or like if this is, okay, so rather like this thing inside is either 0 or 1. So the only thing you have to do is to check that this holds when this is 0 and when this is 1. And it turns out it does. So it's not like it might have taken some insight to see it for the first time, or most likely did, but it's not a hard thing when you think about it for some time, because this can only be 0 and 1. So you start with that, and then you switch order of product and sum exactly as Christoph did, and then you get something useful. And for the Ising model, you will essentially have exactly the same thing. So the random cluster model, when you do this for the Ising model, is another probability measure that for the Ising model with parameter kappa looks like 1 minus e to the minus 2 kappa. Okay, I should write what this measure is called. This will be called phi. And it's on a finite box. So let's write n, and it has the parameter kappa. And this will be a probability measure on sets of edges. And now we can think of them all as being positively ordered. And the measure will almost be bond percolation. Almost. So it will be E1 minus e to the minus 2 kappa to the power of the number of edges times 1 minus that, so e to the minus 2 kappa to the power of the number of edges kind of not chosen. So just this could have been Bernoulli percolation with parameter 1 minus 2 kappa. But then you get an additional weight in the random cluster model, which is 2 times the number of connected components. And connected components here refer to that, like this will be some kind of measure on sets. It will typically be a random set of edges. And in a random set of edges, you can look at the connected components, and here you get a weight according to the number of connected components. And this is not a probability measure if we don't normalize it, because this kind of ruins the probability measure part. So we need to normalize this by some kind of normalizing constant. But then it's a probability measure. And this is called the random cluster model. And it's been extremely useful for the Ising model. And one of the very nice things with this model, in general, is that for the Ising model, if you try to look at the spin-spin correlation, so the product of two spins, and I'm using the typical notation for the Ising model without differentials and stuff, then this is the same thing as the probability that in this random set of edges, these 2 points will be in the same connected components. Or component. Which is kind of nice, because that gives you something about something that's almost a percolation model, which is perhaps easier than looking at the whole Ising model, which is a complicated model with clusters and stuff. So that is called the random cluster model, or the Ising model. And what could be useful with the random cluster model is that if, okay, skip that. So that's that. So that's a random cluster for the Ising model. Now we can do exactly the same thing for lattice gauge theory. We could copy exactly the same proof and make no difference at all. It's just exactly the same proof, introducing it. And get another measure. And so now this is a measure on plaquettes. Because if the Ising model was on something for edges, this should be something for plaquettes. And what you get is almost the same. 1 to the minus e to the minus 4 beta. And this is just because I think I counted edges once there and twice there or something. To the number of plaquettes in the set times e to the minus 2 beta to the number of plaquettes not chosen. So far this looks again like plaquette percolation. But then times a factor that is kind of strange. So we don't have the 2 to the power of the number of connected components anymore. We have the size of a set of all sigma in omega 1, so 1 forms. Such that d sigma on the set of plaquettes is identically zero. So what I mean by this is that sigma is such that d sigma is 0 on this whole set of plaquettes. It doesn't really correspond to anything else in lattice gauge theories, and it's like a strange condition, but it's what you get out of this thing. If you really like algebraic topology, it turns out that the number of connected components is called something like the 0th Betti number. And this turns out to be equal to 2 to the power of the first Betti number. But if you're not very comfortable with Betti numbers, it doesn't really help. It's 2 to the power of something. like that's 0 and that's 1, which is kind of nice, but I mean, it doesn't really help you if you're not comfortable with that. But this is some kind of number that is 2 to the power or something. And apart from that, it's very similar because you have the same population part. And since you have this strange thing here, we need to normalize it somehow. So this is a version of the random cluster model. And what's nice here is that in the gauge theory, if you look at the action, we have beta here. So if beta is really, really small, this is very noisy, that's high temperature. But if beta is really, really small here, then we have almost like 1 minus 1. So this is low temperature. So in the regime where we have a lot of noise here, we cannot have that many packets here. It's kind of a sparse model. So for that reason, it's kind of doing the same thing as Christoph's dual model did for him. Namely that I go from a high temperature model, when beta is small, to a low temperature model here. So that's why this, you could expect that this could be useful to understand what's happening when beta is small, because then this should be nice. The next thing we need to do is to translate the observable. This is also, to some extent, analogous to what Christoph did. Our observable now is our Wilson loop. So that needs to somehow be translated. And again, this is not hard. If you look at the proof for the Ising model and try to copy it, this will always fall out. So this is really analogous to the Ising model. But the observable you get is that this is now equal to, in the random cluster model for packets, the event that there is some subset of the random set of packets such that the boundary of P prime is equal to that. So what that means is that you have this random model that will just give you a random set of packets with some kind of property being like preferring this, like being nice in the sense of the Betti numbers, but still some kind of random set of packet. You could get any random set of packet. So the event you want to consider is that somehow in this very strange set of packet, there is a random surface of some kind of shape that happens to have gamma as its boundary. Now, so the first thing that is very nice with this, again, is that what was high temperature before is now low temperature. That's kind of always good. That's kind of what you're looking for in an expansion. The other thing that is better than you might expect it to be is this part. And the reason this part is better than you think is that in one of the models I mentioned on Monday, packet percolation, there is an observable that has, as a like regular packet percolation, without this horrible term that is hard to understand. If you haven't had that, then it's packet percolation. You just pick packets independently of each other. There is an observable, like there are several observables there that are known to have phase transitions. You can look at several different things. But one thing you can look at is this. And this was done in a paper from the 80s, I think, by Ising, Russo, Chase, and Chase. And I hope I'm not missing someone. We looked at exactly this observable in packet percolation, which is now kind of related to this because we're, again, almost doing packet percolation. We just have this additional horrible term. They look at exactly this, and turns out that it has a phase transition in packet percolation from area law to perimeter law, which is kind of very nice. And if we skip this horrible term for now and just think about why that should hold true for packet percolation, essentially the reason in the two extremes is very simple, and it's the following. So if you have packet percolation and you have loads of packets, like almost all of them, then you will have one infinite component. This is usually what happens in any type of percolation if you have a lot of stuff. You get one infinite component. So that means that if you just pick a random like set of packets, you will almost have a giant surface spanning them already. There might be, because you're unlucky, that there are like some packets missing kind of close to the boundary, because that will still happen with the positive probability, but there will not be too many of them. So essentially what you have to do if there are loads of packets is to kind of connect this boundary to this infinite cluster, close to the boundary. So that should give you a cost that's kind of proportional to the length of the boundary, hence perimeter law. On the other hand, if packets are extremely expensive, in a typical configuration you will have almost no packets. So then these events should be a very small probability because there is nothing there to help you in a typical configuration. You really have to add a whole surface, and then you will typically pay the cost of a whole surface, and then you get area law. And you can do a similar argument to what we did before the break to get that, to show that you actually get area law in that model. So in a related model, packet percolation, has a phase transition from area law to perimeter law. Again, for this natural reason, either you have a giant component there already that almost kind of spans the loop, you just have to attach your loop to it by adding a few things close to the boundary, or you really have to add a full surface and then pay for the whole surface. That drives it. But packet percolation has it, and now we have a model that is kind of almost packet percolation. We have this additional kind of bad thing, but it's almost packet percolation. So then the question is, like, how far are we from actually doing packet percolation? Because if we could say that we were kind of really close to packet percolation, then we should be able to kind of inherit this behavior of packet percolation, this perimeter law to area law that we think our subfunctional models should have as well. In fact, they actually know it's sharp, at least in dimension 3, for packet percolation. So the question is, like, how far, how much does this term ruin it? Like, does it ruin it a lot? Is our model really far from packet percolation? Or are we kind of close to packet percolation? So again, that was 2 to the power of something that was called a Betti number. And you don't really need to know the Betti numbers. It's just that, like, the 2 will kind of explain why I use 2. You can also just think about that thing, although it's a bit strange. It is like you want the 2 form to be 0 on exactly units of packets, and it's not something we discussed so far. But anyway, we have that thing. Now, so the main question now is, how far are we from packet percolation? And a typical way to see how far we are from packet percolation is to think about what happens if we do a Gibbs sampler. We were discussing Gibbs samplers over lunch. Gibbs samplers are nice. Gibbs samplers are something you typically use when you want to simulate systems like this, like big lattice systems. And the whole idea is that you pretend you kind of forgotten the spin at some site, and then you resample that according to the stationary distribution. Then you have a Gibbs sampler. You can do that a lot of times. In this model, if you try to do that, or think about what happens if you do that, well, you would kind of almost resample it according to packet percolation, kind of almost. But then you would need to worry about how much this strange number could change when you did that. Like, how bad can it be to resample a packet? And it turns out, which is very nice if you think about it for a while, that it can most change by a factor of 2. So that, like, the main result, see if you can read it here. And I just realized I also promised not to forget to put the lights on. So good morning to everyone that's there. Yes. So it turns out that the worst thing that can happen up there when we resample the value of a packet is that that factor over there can change by a factor of 2. So it can either double or be the half of what it was before, but it can be the same, but it cannot change by more than that. So worst case, we're losing a factor of 2. That means that the measure we have, which we kind of like except for the fact that we have this strange thing there, is stochastically dominated by, and stochastically dominates something in Bernoulli percolation. Because now we can say how bad it is in worst case to kind of resample a packet to something, and how bad it is kind of in worst case. And this gives you that this is stochastically dominated by packet percolation with parameter 1 minus e to the minus 4 beta. And it stochastically dominates packet percolation with parameter hyperbolic tangent of 2 beta. And this is very good. And you can plot them and see that they are different. I think. Did I make a mistake?
What's this? I.
Ah, okay. Yeah, so this is a measure on random sets of packets. Right? It's that measure. That measure.
Ah, with an N. I think the.
Oh, right. Good. Thank you. I was slightly worried. Yeah, so it's stochastically dominated by Bernoulli percolation on packets, and it's stochastically dominates Bernoulli percolation. So, I mean, these parameters, depending on beta, might be very far apart, but we don't really care too much because we're not getting anything sharp anyway. It's sufficient to inherit this for small beta and for large beta. So this, in fact, shows that the model must inherit area law and perimeter law from packet percolation. It doesn't make it sharp, and the reason it doesn't make it sharp is that we said that if beta was, say, really, really large, that was a reading where we had perimeter law before, then that thing will be close to 1. So almost all packets will be there. So we have this attachment cost. But the problem is that even though this is sharp, to use this result from packet percolation, we have to use the lower bound, if we want to get the lower bound. So then we can get a perimeter law like a bit away from the critical value for that, because we have to be above we need this to be above the critical value in packet percolation. And on the other hand, when we want area law, we want this thing to be lower than the critical value for packet percolation. And since these are not the same, we'll get a gap. But still, this proves that the model must have area law and perimeter law, simply because it inherited it from packet percolation. And as far as I know, all the proofs of area law uses some version of this, not the random cluster model, because it exists only for Z2 and Z3 as of now, because the result that it even worked is just a few years old. But if this does not exist, you can use, say, high temperature expansions to prove the same thing for all finite groups, or have Fourier transformations or something. But it's not as nice as this result with the random cluster model. But it kind of works. Like the bad thing with this thing, apart from that it's not as general, is that this gives you no real intuition for why this should happen in the original model. So like the argument with moving the surface gives you some intuition for why you should have perimeter law. This kind of does not. It just says that somehow the dual model is related to packet percolation. Things are easier to prove there, and hence it follows. The other reason this is not like perfect by any means is that what one would want to prove is that, like now we have this line from beta going to infinity, starting at 0. What we have proven now is that we really do start with area law for small beta. So up to some kind of point, beta 1, we have area law, or area decay, and then there is some point beta 2, where we have humidity. And it's kind of believed they should be the same, but there is no way this proof will ever give that, because this bound is kind of ruining it. Like I can't bound them from above and below by plaquette percolation without having a gap. So it will not work. But again, this is an open question. It's known for Z3 that they are the same, and that result is from last year. So this is kind of hard things, but it's not known for Z4.
Who did that in Z3?
What?
Who wrote paper on Z3?
Paul Duncan and Benjamin Schweinhardt. I think one of them is now in the States somewhere, and the other one is in Tel Aviv. I think, or in Haifa, perhaps, at least in Israel.
So in 4D, the beta 1, beta 2 are explicit or implicit?
In 3D is where they are known to be the same.
In both 3 and 4D.
So in 4D, there is a guess for what the value should be if they are the same, because it turns out that one thing you can show about this model is that it's self-dual. And then it would be natural to expect that if it has one phase transition, it should happen at the self-dual point.
And 2D Ising.
Yeah, and then you could calculate what that is. However, there is no proof that puts them even kind of close together. So it's really just a guess. So I mean, it would naturally be there, but at this point, no one even knows. Like there could be another regime in between with another different behavior. It's not known. It's believed to not be the case, but it's not known. In Z3, I think they know what the point is.
So in 4D, the beta 1 and beta 2 are also implicit.
Yes and no. Like if you know what the point of a phase transition is here, I mean you can translate that to these points and then get bounds, like say that it has to be smaller than this, larger than this. But since we don't know what any of them are, like no argument is sharp so far, so it's really not known. So I guess that this one is one of the like math questions of the model, even if you think that this is not a like physically motivated model. From the math side, it's kind of like it feels like a thing one of the things we should know. Or that it's a very natural question to ask, but it's not known. And the argument for Z3 kind of uses that if you have plaquette percolation, and plaquette kind of something, that kind of plaquette percolation that appears in the random cluster model, plaquettes are in 3 dimensions, plaquettes are dual to edges. And more things are known about bond percolation than about plaquette percolation. And they somehow manage to leverage that. And also in 3 dimensions, in some sense, gauge theory is dual to the Ising model. Because one has kind of vacuum plaquettes, another one has. So you can kind of do things like that in 3 dimensions that do not work in 4 dimensions. So their proof cannot be extended to 4 dimensions. They would need to do something completely different. Yes.
If you knew that the transition is not sharp,
Yeah.
do you know what you would expect in the middle zone?
No. So, like physicists believe it's sharp. Like strongly believe it's sharp. So I mean, again, there's a lot of papers published in physics on this in this area, like at least 10 a day. A lot of them are simulation studies, and there is nothing at all that would suggest that this is not true. But it's not. I haven't even seen. So I mean, they seem to know that there is a sharp phase transition. And in plaquette percolation, again, there's like this phase transition is sharp in plaquette percolation, but what's kind of tricky with plaquette percolation is that there are several different observables you can look at. And at least in high enough dimensions, meaning dimension has to be at least 17, you can show that it has, like, there are natural observables that have phase transition at distinct points. So there is not only one phase transition, there are several of them. And then things like, if there is an infinite cluster, can there be more than one? Like, can there be both an infinite cluster in the set that's there, but then also one in the vacant set? Stuff like that. Like, the phase structure is much more complicated than that with bond percolation. So I guess that would not rule it out, but yeah.
I wanted to make my question a bit more precise. Suppose you have a regime where you have enough energy to have macroscopic flux lines, but not arbitrarily big.
Yeah.
So you cannot reach to the center of the rectangle, but you can somehow reach a part of the area but near the boundary. But that's probably.
I don't know.
In the case of the Ising model, there is this nice coupling between the FK, or the random cluster model, and the spin field, which boils down to putting one ideal spin per cluster.
You have exactly the same thing. It still works.
But I guess you don't just put one spin per cluster of brackets. What would you...
Something like you would look at all the closed forms that have support on a subset of these packets, and then you would pick one uniformly at random, which is of course a pain. You would need to think about, so in they do that in one of the papers by Duncan and Schweinert. They have, I think, 2 or 3 papers from last year and then one from the year before. And they do that in there, and what you need to do then is somehow find a basis of the set of all things that have support in a given set of packets, or a 0 on a given set of packets, but of course that's kind of complicated.
But is this why the Betty number comes up somehow?
The Betty number somehow comes up from the fact that this is a totally natural thing to look at in algebraic topology.
So it doesn't relate to the sampling?
No. Okay. And the sampling doesn't need the Betty numbers. In one direction it's like keep packets randomly, yes, as you would for the Rod-Sokal coupling, and the other direction is like pick a uniform thing somehow. It's just a question of how you do that, and it's not obvious. But in theory, it's the same thing. Or like to an algebraic topologist, it's the same thing. More questions?
I think for the one in placket percolation, do we know things about if I want to look at W gamma 1, W gamma 2? So you translate this into your placket percolation model. Do people know how this behaves?
Like this one?
Yeah, when you
have 2 loops.
Yeah, exactly.
Yeah, so the first thing you would need to think about is the fact that the expectation value of a loop is now not 0, as you have in the Ising model. So it's not as obvious that that's the relevant thing to do. I think you want to look at the truncated correlation function. And then it's not as easy to do it through here. You can go through the random current expansion and then kind of translate that to here to actually get a probability. Because essentially a strange thing with kind of Wilson loops is if that you have 2 ones and look at the same thing. So you have one loop here and one loop here. And now there are 2 ways to connect them, or like to have these as a boundary of a surface. One way would be just to like pick one surface for this loop and pick one surface for this loop. So there's no like requirement that they are connected. So that is one way to do it. The other way to do it would be to connect them by kind of a tube that has these 2 as like, so there's 2 different ways to connect them and have them as a boundary. And the idea with looking at truncated correlation functions would be to like exclude these screen things, so you really would force the model to have a tube. But you need to look at the truncated ones to do that.
So is anything known about the correlations between different ones?
Yeah. So for large beta, there are papers. So I have a paper from a few years ago on using lattice wave theory for large beta, and it doesn't have to be crazy large, so it's not a legitimately large. but you have to have finite clusters, and if you have finite clusters, you have exponential decay of perturbations. And then essentially it follows from, if you use the random current expansion, you would see that you have, for this tube reason, you would have exponential decay of perturbations for small data as well. But not for like increasing reasons, just for trivial reasons. But again, this is all away from the perhaps one critical value. So there's a lot of things to do if you like lattice systems.
Loops that are non-trivially linked, is there anything you can say? Or is it just more complicated?
More complicated loops?
If loops are linked.
Linked loops.
I guess it's just not
No, but it's a nice question. I haven't seen anyone do anything like that. Like the heuristic of removing things not close to the boundary would still work if these are like really, really large loops. So I guess you would still get perimeter law in some regime for that reason, like with that heuristic. And then I guess it also might depend on which dimension you're in, because in 4 dimensions, 2 loops that are linked are not really linked. Yeah, no, so I haven't seen anyone do it. So, but obviously you should at least get perimeter law somewhere. And I guess also here there is nothing that, like for this argument, you do not need the loop to be nice. There is nothing in this argument that requires the argument to be nice. The random cluster model works anyway, and this upper and lower bound works anyway. So I guess the first model to think about this in would be packet perturbation.
Don't see any more questions. Maybe let's thank Malin.